Hello everybody, my name is Nathan Brophy, and I'm here to talk to you today about the IBM Container Software Security and Certification Program, and this is how IBM makes cloud-native workloads safe. So let's dive right into it, talk about the Container Certification Program IBM provides, and look at some architecture and details about this. It's a set of over 150 certification requirements, best practices, and standards, and all IBM Container Software is certified against these standards and held to them. About a quarter of the requirements focus on security, and subject matter experts and certification engineers work together to raise the bar, and we hold IBM software to the highest standards. And what the certification engineers are folks on the team that work with the actual product teams and offerings coming through to ensure that they are in compliance with the requirements. One other thing I wanted to call out here is that the certification program is security first. It's security driven. We can tell that by having almost a quarter of the requirements focus solely on security here. IBM is delivering the most secure hybrid cloud out there today, and we're doing this with the most secure cloud native applications in the industry, and this certification process is at the foundation of being able to enable that. Alright, so let's look at a picture to go over this. So a content team is going to start development on their cloud native offering. One of the first things that they're going to do is integrate to our continuous integration and continuous delivery pipeline. And for those that aren't familiar with the term, that's CI/CD, and we're going to refer to it as that for the rest of this. Then they're going to build on common certified samples and components. So we have a bank of certified components that are for use by product teams coming through. It quickens development time and it ensures commonality and certification throughout the development lifecycle. And then they're going to start the IBM Container Certification when they're at a point where they're getting ready to release their product. So the review of that software is going to start, and then that software is iterated on in a continuous integration fashion in our pipeline to comply with these requirements. So the first time an offering comes through for certification, they might be out of compliance with 10 or 15 of our requirements. So then what happens is that product team works with the certification engineers and the subject matter experts on the team to come up with a way to get in compliance with the requirements, and then that software is iterated on and iterated on and iterated on until eventually it's able to get granted certification when it comes into compliance with our requirements. And then once that certification is granted, that software can be shipped. And I just want to point out here that if you look at where the starting of the IBM Container Certification starts and the integration to our CI/CD pipeline, it's baked into almost the beginning of the workload's development lifecycle. So our certification process is baked into the development of the offering from the very beginning. Now I want to take a little step forward here and give you all an idea of what the benefits this certification program brings to the table. So our certified software is vetted against over 150 requirements, and almost a quarter of them are security related. So software must also, as part of this, undergo a review from the Security and Privacy by Design, or SPVD folks. And that's a team here, and they do a further threat analysis of the workload. And a cluster admin can quickly see if a workload is secure. How can a cluster admin quickly see if a workload is secure? Because they know that that software has been certified against all of our requirements, and they have an expectation of what the security posture of that offering or workload is. And we also provide a packaging mechanism called case, where this is all explicitly clear for an admin as well. And towards the end of the presentation, I'm going to do a little bit of a deeper dive on case, so stay tuned for that. And all of our container images are scanned for vulnerabilities with multiple scanners. All of our container images are expected to be Red Hat certified, and as part of that, they are ran against the CLAIRE vulnerability scanner. And inside of our own continuous integration pipeline, the IBM Vulnerability Advisor is ran as well. And using the IBM Vulnerability Advisor, the container images scans are visible to the workload teams throughout the lifecycle and through the process of certification, and that scan is continuously happening on a daily, weekly basis to figure out if there's any known or serious vulnerabilities in that container image. So that way remediation actions can be taken and security fixes can go out for those images. So that was a couple of the benefits of the certification program. From a security perspective, there's many more from a quality assurance, product readiness, just general good health of the product, storage. There's a lot more that goes into the certification program that you get benefit from. I'm just going to focus on the security aspect. So with that being said, let's dive into the principle of least privilege. So what is a principle of least privilege? Well, this is a design doctrine, and it's at the core of the IBM Container Application Certification Program. The principle of least privilege is a driving factor for a lot of the requirements inside of our program. So let's take a look at what this is. The principle of least privilege states that you shall only use the privileges needed to execute the given task. You deny any privileges outside of this set, and you have a clear separation of roles and duties throughout your application. It's easier said than done, and it's easy to say this and keep moving on. So what I want to do is dive into a picture and a visual illustration of what this might look like. So let's say that you have an operator, and the install of the operator requires a cluster admin, and that operator needs to be deployed using the privileged SCC. And this is assuming an OpenShift cluster. So let's say the operator is laid down. Here's the pod running the operator controller. Here is a service account with the RBAC and SCC bindings for it. And then, so now on your cluster you have an operator up and running. Now what we want to do is actually instantiate an operand pod, or we want to instantiate an instance of the operator here. So a namespace admin or a developer, so now we're switching our persona, is going to submit a custom resource or CR to the cluster, which has configuration details and the necessary information needed for this controller to actually stand up an operand. So the controller is going to intercept the CR, come out and deploy an instance of that, and install the operand to the cluster. Now the operand pod doesn't need all these extra privileges that the operator does, so it just runs under the restricted SCC, and it has its own service account and role bindings for that. So if we look at what happened here, we have a clear separation of roles and duties. One role is a cluster admin, and their job is to install the operator, and the operator's job is to look on the cluster for these custom resources and reconcile those. We have another role, which is the namespace admin or developer, and their job is to stand up an instance of the operator or the operand here. And each of those roles requires different privileges, and we can see that through the separation of different service accounts bound to different security context constraints. So why is the principle of least privilege important? Well, containers are nothing more than processes running on a shared host operating system. And there's many features that allow for container breakout: host file access, host processes, and access to the host network. And when an application breaks out of a container, any other container running on the same node or network can be compromised. And now we're going to take a deeper look into the requirements and architecture that go behind the security certification requirements. I want to give a little background on container isolation and Kubernetes as well, because this is going to be an important topic we talk about later. So containers are isolated on Kubernetes with the following. So a pod is the unit in which a container is scheduled on a worker node for Kubernetes and OpenShift. Kubernetes uses a construct called pod security policies, or PSPs, to restrict the privileges a pod can request and access. And these policies are applied and bound to pods using role bindings and the declared security context within the pod definition itself. OpenShift, on the other hand, uses security context constraints, or SCCs, and they use those instead of pod security policies. Now, the capability between the two is nearly identical, but SCCs provide a few additional protections. The pod declares the security context that it requires inside of its security context spec definition for the pod and the container, and then the policy, or SCC, then enforces that context. So if you are using a user that has let's say the restricted SCC bound to it, and you try to stand up a pod that has a container that needs root access, or privilege escalation, then the enforcement of that policy is going to deny the scheduling of that pod because your user doesn't have the authority to do that. And this picture is going to describe what container breakout might look like. So we have a cluster here. We have 3 nodes. Each node there's namespaces, and now let's look at this pod. So this container, highlighted in green right here, is isolated. It stays within its own confines, and there's no breakout. This container, on the other hand, needs access to files on the host node. It also needs access to the host network, and it needs to know what processes are running on the node to function as normal. And this isn't great. This is container breakout, so now this container can go out on the node and see resources on the node like the file system. So that means that if this container uses persistent storage on that node, then you have to assume that this other container in red here can see what this container is doing. And this is called container breakout, and it's not a great situation, which is why part of the certification program moves towards container and pod isolation. And with that, let's transition into isolated pod security. So we at IBM are moving towards pod isolation, and this is achieved through using a restricted security context. Now, workload pods must run with the restricted SCC, and when the restricted SCC can't be used, you have to use the most restrictive SCC as possible. And the security context for pods must be explicitly defined, providing a clear security posture. So that means any privilege or toggle for security that your pod needs, whether it's on or off, has to be explicitly declared in the pod and container spec, so that way there's no ambiguity when matching the pod for a valid SCC and at admission time for scheduling. There's no ambiguity on what the security context and posture of that pod is. So let's take a look at this picture over here that shows the OpenShift default provided security context constraints. The most restricted one offered is restricted. And from there, the next step up is non-root, and this can be seen as restricted, except non-root allows you to run as any user you want aside from user 0, or the root user. The next step up is any UID, and any UID is essentially non-root, except it allows you to run as the root user. You can run as any user ID you want. Next step up from that is going to be the host path, and host path gives you access to the host path. Next step up from that is host network, which gives you access to the network the pod is running on through the host node. The next step up from that is going to be host access. So this gives you full access to the namespaces inside of the host. And the next step up from that is privileged, and privilege gives you full access to the host. When you run as privilege, you get access to basically whatever kind of permissions that you're looking for. And at IBM, through the certification process, we're trying to move all workloads towards using this green box here, the restricted box. So what arbitrary user assignment allows for is pods to run containers under an arbitrary user ID. Now, OpenShift allows for runtime user ID assignments in containers, and that's the default behavior you get with the restricted SCC. The user ID is chosen from a range specified in the namespace by a namespace administrator, and if there's no specified range from the namespace administrator, the OpenShift runtime will create a range for you. And when your pod is scheduled and it stands itself up, the OpenShift runtime then sets the UID for that pod and that container from a range in the specified namespace. And that user ID is guaranteed to be safe from collision on the host when running in different namespaces. And this adds additional isolation between pods running on the same node and different namespaces, because you can guarantee that the users your containers are running at are going to be different, unique, and safe from collision when doing this. Now I want to talk about network policies. So a network policy is a Kubernetes native resource, and OpenShift provides additional support for this. However, some of the features for network policies that Kubernetes supports aren't fully supported in OpenShift yet. And the resource, what it comes down to is it's a software-defined network or firewall, and it provides additional pod isolation through the network traffic that it can receive and send. So a network policy allows you to define rules for ingress, egress, and pod to pod or service to service. And one way to think about this is where your SCC provides a firewall around the container process, your network policy creates a firewall around the actual container network. So let's look at a picture for this to get a better understanding. Here we have a cluster that's this light blue dashed line rectangle. We have a network policy, that's the darker blue, and we have a bunch of pods. So let's start with the pods and then we'll get to the external connections. We have pod A in the top left here and pod B in the bottom right here. Pod C tries to make a network connection request to pod B. And we see this green arrow indicating that the network policy explicitly states that this pod can receive traffic requests from this pod. However, this network policy does not allow for this pod to receive any network connection requests from this pod. So we see this red dashed line arrow, which means that this network request is denied by the network policy. And these two pods out here have no permissions or rules in the network policy that allow them to make connections to these pods. And now let's look at an external connection request from outside the cluster. So now we're looking at an ingress connection instead of a pod-to-pod or service-to-service connection. So this external connection request comes into the cluster and tries to talk to one of these two pods. This network policy here does not have this external connection request defined or explicitly allowed. So that means this network connection request is not allowed to happen and is denied by the network policy. Now let's say that this pod here is sending some data to an external data store or doing some sort of backup recovery process. It needs to make an egress connection to an external connection. This network policy explicitly states that this pod is okay to make that connection and send the data. Now, if this pod were to try to make an egress connection to, let's say, this external request up here, that would be denied by the network policy because there's no enforcement for it specified. So the way that IBM uses the network policy inside of its certification program is we dictate that all workloads must provide a network policy that explicitly declares what their expected traffic is, so that way you are only receiving and sending the expected traffic in your workload for your pods, and any unsolicited or unexpected traffic is denied. And it gives you a firewall around the workload. So any data, when it's in transit or on the wire, that includes virtual and real traffic, must be encrypted using TLS 1.2. And this is the end-to-end data in motion encryption, and it's a requirement of all workloads. And I just want to call out specifically here that this does include intra-cluster or pod-to-pod or service-to-service communication as well. So let's say pod A talks to pod B on the wire using HTTPS or HTTP. This has to be done with TLS 1.2, so we're going to force it to be HTTPS to encrypt the data. And some people might think, well, if it's just pod to pod and it's on the cluster, it's safe to use non-encrypted. It's safe to use HTTP, right? Well, that's not entirely correct. It's actually dangerous. So let's say pod A and pod B and pod C are all on the same cluster in the same namespace, and they're all talking to each other over HTTP and not using TLS 1.2 to encrypt the data. A noisy neighbor or somebody else can be sitting on the cluster and just listening for that traffic connection. Even though it's pod to pod, they can still intercept it like a regular traffic connection request and view all that data, and it's going to be unencrypted. So that's why we require any network connection and any data that's transferred on the wire to be encrypted using TLS 1.2. And we also require non-system namespaces. So your offering or workload or application should be able to run inside of a user-defined namespace. And there's a set of system-defined or special OpenShift-defined namespaces that are privileged. And I want to call those out because these don't treat SCC policy enforcement the same as a regular quote-unquote user-defined namespace would. So those key namespaces are Kube system, default, and the OpenShift star ones. And there's a few exceptions for the OpenShift star ones. Especially with Kube system, the SCC policy enforcement is not honored in the same way. So you could think that your workload is running with a restricted context in Kube system, but in reality it has privileged access to whatever it needs. So we force the workloads to be installed and runnable in a user-defined namespace where the SCC policy enforcement is treated as you would expect. Unique service accounts per workload are also required. And when I say unique service account, what I mean is you're not using the default service account that comes in a namespace. So every workload has to provide at least one unique service account, more like the operator example we went over before where there was 2 service accounts depending on your separation of roles and duties. But there has to be at least one unique service account and the role bindings needed to use it. So the use of the default service account in a namespace is usually prohibited, and there's a reason for that. So a service account can have multiple security context constraints bound to it. So let's say the default service account in the namespace has restricted, any UID, and the privileged SCC all bound to it that it can use. Then that means that anything deployed through that service account or anything ran under the authority of that service account inherits the union of all privileges bound to it, which in this case would be the union of the privileges granted by restricted, NUID, and privileged. So basically you have to assume everything is privileged, which isn't great if your workload just needs restricted, and that's a violation of the principle of least privilege, which is why we require unique service accounts. And so just to wrap that up, the workload must provide a unique service account for each unique security privilege domain. So going back to that operator picture we had before, there is a unique service account for the cluster admin and a unique service account for the namespace admin or developer. And this provides a reduced threat vector through having only the privileges required for that task. Now we've talked a lot about security context constraints and how there's some default ones that are shipped with OpenShift, but we at IBM force all of our workloads to provide a custom SCC. And there's a few reasons for that. One, this SCC has to be an exact match to the workload security posture. So in the spirit of the principle of least privilege, this SCC marks exactly the privileges it needs, no more, no less, but is an exact match for the workload security posture. And this gives a clear view to a person installing this what that security posture is. And you have a clear definition of all required privileges. And the custom SCC is expected to be bound to the unique service account of that workload. Now, the other part of this is defensive coding. So if you provide a custom SCC, you separate yourself from the platform-defined default, which say you're running an OpenShift 4.4 and then 4.5 comes out and one of the default SCC definitions change. Having a custom SCC protects you from that. It separates you from the platform-defined defaults. Now, our workloads have the option to run with OpenShift native SCCs like restricted, NUID, and non-root. However, we still require the custom SCC so that way you get an installer can see the clear view of the security posture and that workload is separated from platform-defined defaults. Now I want to call out encryption at rest too. So persistent data that's handled by the workload, it all has to be encrypted at rest. And there's a few types of encryption we can talk about here. There's active encryption and passive encryption, and we prefer active encryption. The difference is when you're using active encryption, it's the onus of encryption is on the workload. So the workload encrypts that data before it goes into the persistent store, and then it takes it out of the persistent store encrypted and decrypts it for its own use. So that data goes in encrypted, comes out encrypted. Passive encryption, the onus comes on the cluster administrator or the person consuming the workload to encrypt the data in the persistent store. So data goes into the database unencrypted, and then some daemon process like Lux or some other product out there will come through and encrypt the data passively in the persistent data store as it sits. So at the end of the day, you still get encrypted data in the persistent data store. The only difference is when it gets encrypted and who's responsible for the encryption. And so if you take a look at this encryption at rest requirement in combination with the requirement to encrypt data in motion at TLS 1.2, you can see that all IBM container software products are using encryption everywhere. Your data is safe and protected. Now let's talk about keys and certificates. So IBM encourages a bring your own key and bring your own certificate model. It's your data that you're putting into this product, so you should have the option to protect it with your own keys and certificates. One thing that we strive to do as well is follow public key infrastructure best practices. So what that means is when a customer brings a certificate authority or CA signed certificate into the cluster or workload, the workload that consumes that has the responsibility of making sure that that certificate is valid with the CA. So they check the signature and they check to make sure that that certificate isn't revoked. And they do that through the CA's CRL using the OCSP protocol. And it's up to the workload to do their own due diligence to make sure that the certificates that the customer brings are valid through PKI best practices. And just to continue on that, we encourage a bring your own key and bring your own certificate model, but all your workload should still function without the need for customer keys and certificates. If the customer doesn't care about this and doesn't want to import their own key or certificate, your workload should be able to handle this situation. And our workloads use secure storage to store the keys and certificates. This includes Kubernetes secrets and IBM Key Protect, which stores key data in an HSM separate from the cluster. And all of our workloads use key and certificate management systems to secure the full life cycle of keys and certificates. That's another one of our requirements. You must use a cert manager to secure the end-to-end lifecycle of your certificate. Well, the information is stored in a downloadable archive called a case, and that stands for Container Application Software for Enterprises. And the spec for this is public out in github.com/IBM/case, and the archive provides a snapshot of all software that's certified in a well-defined format. And the archive is also used as a secure packaging and distribution structure for workloads, providing a command line tool implementation to help. And that command line tool can be found at github.com/IBM/cloud-pack-CLI. And this should also call out this link here where the public specification for cases, so you can dig in and see a little more on your own as well. Alright, so now I want to go over a quick mini quiz and just to see if you think your own container software stands up to some of our standards. And this is going to be a subset of our actual security requirements that our workloads have to go through. So I'm just going to leave this up here on the screen quick so that way you can read through it, pause it, take it at your own pace. And let's take a look at the next page here. That was 10 different requirements, and I want to call out that there's more than 25 additional security requirements that IBM container software products and ISV partners have to go through in order to get their certification granted. And each requirement comes with a how and a why. So each requirement tells a product team you must do this. However, we also provide product teams with the how do I do this and the why is it important. So that way we spread that knowledge across IBM and keep continuing to build on these common foundations. And IBM continues to raise the bar on the requirements. We do this in a continuous integration and delivery fashion. Every month our certification requirements are revamped. So if there's new requirements that come out, those are published at the end of the month. If existing requirements need to be updated or reevaluated, then those are done at the end of the month. And these fixes to requirements, additions to requirements, and any kind of changes on the requirements and the enforcement of that is delivered monthly in a CI/CD fashion. Alright, so that is all I have for you on the presentation today. Again, my name is Nathan Brophy with the Cloud Pak Engineering team here at IBM, and thank you for your time today.